Hello, everyone. My name is Zhong. I'm an associate professor at WPI. So today, what I want to talk is about the application of computational thermodynamics in solid oxide fuel cell. So here I want to give a very brief introduction of a solid oxide cell. So essentially, we will have cathode, electrolyte, and anode. In the cathode side, we have oxygen from air will move through the electrolyte and meet hydrogen, the fuel on the anode side. And with this, we will generate water. Meanwhile, we will generate electrical energy, right? That's electricity. So that's a basic principle of solid oxide fuel cell. And how the thermodynamics actually will play a role here. A very important thing for a solid oxide fuel cell is what is happening on the cathode side, which will contribute the significant part of the long-term degradation. Essentially, your power output will drop with operation time, right? So on the cathode side, what's happening is we will have the cathode and the electrolyte, and a lot of things may happen there. So the cathode and the electrolytes may react with each other, right? So that will form some detrimental phases. And also we will have the air, right? Have a lot of impurities. The impurities will react with the cathode and form some phases on the surface of cathode. And also for the cathode material, you need to have, and also electrolyte, right? So you need to have a very good combination of the electronic conductivity and the oxygen ionic conductivity, right? So all of these, any change on all of these will cause the long-term degradation. Okay, so here I listed the critical issues for the long-term degradation, right? So essentially, this is what we have done to figure this out. So we have figured out how to develop the thermodynamic database and how to do the quantitative defect chemistry analysis and how to predict the electrical conductivity and also the cathode electrolyte compatibility and then the air impurity effect to the cathode and a lot of other things, right? So in today's talk, it is very brief. Hope I can describe the main issue with you in a very high level. So the first one is about the thermodynamic database development, right? So this is what typically what Cathode is doing, right? So we have phase stability and thermochemical data from experiments, and then we will mainly model the Gibbs energy, right? So that will come from the thermodynamic model. And one very important thing we have found here is with the solid oxide fuel cell database, we will check the defect chemistry, right? So if the defect chemistry doesn't have a good match with the experiment data, then the model has a problem, right? So we need to go back to work on the thermodynamic model again, right? If it has a good match on the defect chemistry analysis, of course, the model is correct, the Gibbs energy is correct, and then we have the database. So as an example, what I want to show is, for example, if we have the Nathner cobaltate, right? So this kind of perovskite. So with our model, right, we will model perovskite as AbO3. Right, so in the A side we have Nathner, B side we have cobalt, and here the very important thing is in A side we consider Nathner 3+ and vacancy. B side we consider different species of cobalt, right? So cobalt 2+, 3+, and 4+, and also the vacancy. And for the oxygen side we model the oxygen 2- with vacancy, right? So with this, our model has a physical meaning, right? So it can work with the traditional defect chemistry analysis, right? So for example, right, so this shows you the database we developed, right? So this is for LCO, how the oxygen deficiency will actually change with the oxygen partial pressure and different temperatures. So as you can see, the slope, right, of all these curves match with perfectly with experiment data, right? Not just in the middle here, but also in the very low oxygen partial pressure region, right? So all of this shows the slope itself represents the defect chemistry inside, right? So this shows that we have a very good agreement with exactly what is happening in the ALCO lattice. Okay, and why this? So I call this like the Cathode plus, right? Why this is important? Because as we can plot the broad diagram, I will show you, and also we can predict the electric conductivity, we can predict the phase stability, and also the thermomechanical property, right? So that's why this is very important. So for example, this is a quantitative broad diagram. So in the past, right, people can typically draw the broad diagram by hand, tell you what is happening and the trend of each species. And what we can do here is we can quantitatively tell you how each species actually will change quantitatively, right? So how it changes with temperature, how it changes with oxygen pressure, how it changes with composition. So we have the database, and then we can plot all of those things. Okay, so with that, we can predict the electrical conductivity, right? So actually, it is very simple, right? So people have known this for a very long time. If you want to predict the electrical conductivity, you need to know the charges, you need to know the carrier concentration, and also you need to know the mobility, right? So as long as you have those, you can predict electronic conductivity and ionic conductivity, right? So however, right, the main challenge in the past is you don't have reliable prediction of the carrier concentration. And our Cathode plus approach can provide you that, right? So for example, right, so with the broad diagram, we provide you the manganese concentration, and then that will tell you how the conductivity, right, actually will change with temperature, with change with oxygen partial pressure, right? So as you can see, our prediction has a very good agreement with experiment data, right, and all these conditions. So the advantage of this is if we have a good agreement on those, right? So we can plot a whole region, what is happening, right? So this is just a demonstration how the electronic conductivity is working. We can also working on the ionic conductivity, right? So we have done that as well. Okay, so the next one topic I want to talk about is the cathode, the electrolyte compatibility. And this is very critical because the main reaction we have here is how the oxygen from air will transport change into oxygen in the YZ lattice, right? And this reaction will only happen at a triple phase boundary. So the three phases we're talking about is LSM, the cathode, air, and YZ, right? So you have to have these three phases there, and then you can have this reaction happens. So if there's anything wrong with this point, right? So then the reaction will stop and you will observe the performance drop, right? So in the real case, of course, unfortunately, we do observe bad phases actually forming, right? Like ALZO, right? Natrium zirconates, and the strontium zirconates. And if you check the resistivity, you will find, right, comparing with LSM and YZ, ALZO and SZO actually increase thousands of times, millions times or even billions times, right? So that is huge. So this tells you that even if you have a tiny bit of ALZO, your performance will drop. And this is what people observed, right? So they do observe this kind of tiny particles of ALZO actually forming there. So that is why we have to figure out a way that we can prevent the formation of ALZO. And from the thermodynamic analysis, right, we know that the ALZO formation will need air, LSM, and YZ, right? And there are a lot of parameters there. Strontium content, the A-side deficiency, the E-tron content, the oxygen partial pressure, and many other parameters, right? Like temperature, the microstructure, reaction time, the ratio between LS and YC. All of these will affect the LZO formation. So if you design the experiments, you will realize it is very difficult for you to figure out the mechanism because there's so many parameters there, right? Fortunately, we have the thermodynamic database. We can make the prediction, right? And this is what we predicted, and in comparison with the experiment data. So we found that the LZO and the SZO at low temperature, actually, it will already start to form. And then when the temperature increases to 1200 degrees C, you have a lot. And when you have even higher temperature, you have a significant amount of LZO, right? So there are three stages there. And we did experiments. It confirms that our prediction, the trend is reliable, right? So with this, we can make prediction, right? Like how to optimize the cathode and the electrolyte, all those things. And then to figure out how to control the formation of LZO and SZO. So that will reduce the degradation. Okay, so the last one I want to talk about is in the air, right? So this air impurity actually will also affect what is happening, right? Like those SO2, CO2, water vapor, chromium 6, all those things, right? So as you can tell, right? So all of these has a bad effect to the cathode material, and also they may have this kind of a synergetic effect there, right? So you have multiple impurities. So it is very, very complicated. So what we did is, for example, here we have investigated all of these, but today I want to just show some simple case, right? So for example, like this sulfur tolerance, right? So for the sulfur tolerance, so we have seen that from the simulation, right? So we will have manganese oxides, those small amount, right? Will form and high temperature. So for example, like this 1000 degrees C, if you have the same thing at lower temperature, like 800 degrees C, you have manganese oxide and also strontium sulfate, right? So we did the experimental characterization. It does show the formation of those phases, right? But these are like the SEM, EDS analysis. It may not be that reliable, right? So that's why we also tried the TM analysis. So it does show these two phases actually forming there. And we just recently published a paper on this. So overall, what I want to tell is from the computational thermodynamics, right? So there are a lot of things we can do for solid oxide fuel cells, so mainly on this long-term degradation. And hopefully today I just use this very brief examples to show you what we have done in this project. So at the end, I want to say, happy thermodynamics. Thank you, everyone.